We've seen that working with the production function, and in particular with the simplified form of the production function, the two-dimensional production function, already enables us to say some important things about the process of economic growth. So this observation that the path to economic growth can be different for different economies has some important implications. It has some important implications when we look at some real-world success stories, in particular a debate that has been carried on about what is important, what has been important for growth in the economies of East Asia, Hong Kong, Taiwan, Singapore, for example. There, as we'll see, growth has been fueled, particularly in the early stages of growth, by what's called capital accumulation, by building up, essentially, the capital-labour ratio. So what's the debate? The debate is whether those economies that have experienced economic growth as a result of building up their capital-labour ratios can rely on that continuing going forward into the future. Because of diminishing marginal productivity of capital, what works in terms of generating growth in the early stages of an economy's development cannot necessarily be relied on to generate growth in subsequent later stages of development. And at some point, governments in economies are going to have to think about whether what's worked in the past, growing that capital-labour ratio, will continue to work in the future. And policies designed to promote growth may have to be reoriented towards promoting total factor productivity as opposed to growing the capital-labour ratio. This in some sense is a choice, a strategy choice that all economies have to face. But so far we've been operating at the level of theory, drawing diagrams, writing down mathematical representations. It all makes sense from a logical point of view, but do we actually have any evidence that these ideas actually have any currency in the real world? Is it true that economies in their initial stages of growth relied on capital accumulation, relied on growing their capital-labour ratios? And is it true that more mature economies, economies with longer histories of growth, have relied more on total factor productivity? There is in fact a very simple analytical technique widely used that will enable us very quickly to provide an answer to that question. It's a technique known as growth accounting. And I just want to quickly take you through this because I want to show you some interesting empirical evidence, some real-world evidence that supports the kind of implications and ideas I've been talking about. So growth accounting is a technique. It's a technique that enables us to look at the growth history of an economy and ask some important fundamental questions about that history. In particular, what have been the main factors at work that have produced the economic growth outcomes that we see in the real world? The starting point, and you won't be surprised to hear this, is the production function. Now previously we've just worked with very general specifications of the production function. Growth accounting relies on a very specific form of the production function. By that I mean a very special type of mathematical representation. It's something known as the Cobb-Douglas production function. It's named after the scholars who first developed this idea. And it is one of the most widely used analytical tools across all branches of economics. Now it's going to look a little daunting when you first see it, but remember we're not really doing anything different than what we've done in our previous work on production functions, other than writing down a very specific mathematical representation. Instead of working with a general production function, we're working with a special type of production function. It's not the only type of production function that economists work with. There's a whole family of production functions. This one turns out to be a pretty convenient one to work with, and it is important in this growth accounting exercise that I'm going to describe for you. The mathematical representation of the Cobb-Douglas production function is here. Most of that you've seen before. A is total factor productivity, K is capital, L is labour, Y is output. I've used uppercase letters here, but all of this material, these variables should be interpreted as being real variables. The thing I haven't shown you before, the part of that expression that's unfamiliar, is that term alpha. Now, this has nothing to do with the rate of economic growth that I talked about before. This is an entirely separate concept. Alpha is just a number. It's just a number that takes a value somewhere between 0 and 1. For example, a very typical number that's used might be 0.25. So that's all it is. It's a number that feeds into the Cobb-Douglas production function that enables the Cobb-Douglas production function to very closely replicate real-world features that we see. To convince you of the practical usefulness of this Cobb-Douglas production function, here is a production table that I've constructed feeding different values of capital and labour into an expression that takes the Cobb-Douglas form. And I'll leave it to you to check that the numbers we get out of this exercise are consistent with diminishing marginal productivity and also consistent with constant returns to scale. In fact, you can show mathematically, and there are many textbooks that do exactly this, that the Cobb-Douglas production function, as long as you assume that that number alpha is between 0 and 1, will always be consistent with those two characteristics of real-world production, diminishing marginal productivity and constant returns to scale. The reason economists work so often with the Cobb-Douglas production function is that it is able to mimic what we observe in the real world in terms of those two characteristics. So I'm now going to show you how this Cobb-Douglas production function can be used to undertake a growth accounting exercise. Remember, what we're doing in growth accounting is we want a technique, an analytical tool, to enable us to examine the economic growth history of an economy and to determine what have been the most important factors that have contributed to that economic growth. So here I've written the Cobb-Douglas production function for you. What I'm going to do is put a little superscript T next to output, next to total factor productivity, next to capital, and next to labour. Because I now want to make it perfectly clear that what I'm talking about is a production process that takes place over a period which we will call period T. If I do that, I can then also do exactly the same thing for output, not in period T, but in the previous period, which we'll call period T minus 1. So period T could be 2013, T minus 1 would be 2012. So the output in the previous period must have been generated by whatever total factor productivity was in the previous period, times the previous period's capital stock raised to alpha, times the previous period's labour raised to 1 raised to 1 minus alpha. And now I'm going to draw on some of that mathematics that I showed you earlier about what happens when you take a logarithmic transformation of an economic relationship. Now again, I don't want you to be too stressed out about this if it's been some time since you've studied high school maths, or if all this looks a bit strange to you. It's the result, the bottom line, that I want to focus on. So if you're a bit unfamiliar, a bit rusty on what it means to take a natural log of a variable, then I wouldn't worry too much about it, as long as you appreciate where we get to when we make this mathematical operation. So let me take the natural log, and we'll go back to this first Cobb-Douglas production function of output in period t. That can be written as the natural log of total factor productivity plus alpha times the natural log of the capital stock plus 1 minus alpha times the natural log of labour. And I can do exactly the same logarithmic transformation for the previous period's Cobb-Douglas production function. So on the right-hand side, we'll have the natural log of total factor productivity in that previous period plus alpha times the natural log of capital in that previous period plus 1 minus alpha times the natural log of labour in that previous period. Well, why bother? Why do that? I want to do that because I want to subtract those two expressions. I want to look at, in other words, the difference between the natural log in period t and the natural log in period t minus 1. If I do that, natural log of output in period t minus the natural log of output in period t minus 1. What do I get on the right-hand side? I'll get the natural log of total factor productivity in period t minus the natural log of total factor productivity in the previous period plus alpha times the natural log of capital period t minus alpha times the natural log of capital in period t minus 1 plus 1 minus alpha times the natural log of labour in period t minus 1 minus alpha times the natural log in period t minus 1. And let me just quarantine a bit of this slide so it doesn't become too confusing for you, because we have in fact just about finished. Because remember, if you take the difference of, let's write it as difference of variables when they're expressed in logs, what you actually end up with is the growth rate. Remember, that's true if our variable is growing at an exponential trend, which economic variables almost always do. So what we have in this expression here, on the left-hand side we have the difference between the log of output this period and the log of output in the previous period. That in fact is the growth rate of output. And on the right-hand side, when we take the logs of total factor productivity this period and total factor productivity in the previous period, and take the difference between those two logs, that's the growth rate of output. That's the growth rate of total factor productivity. Just as a shorthand notation, let me write that as the percentage change in total factor productivity. So remember, the Greek letter delta is my shorthand for change. Next, we have Next we have alpha. Now here we have the natural logarithms of capital this period and the previous period. We're looking at their difference, so we have alpha times the percentage change of the capital stock, or if you like, the growth rate of the capital stock. And similarly, when we look at labour, we have 1 minus alpha times the change in labour, times the change in the natural log of labour this period and the natural log of labour in the previous period. That's the growth rate in labour. And what you're looking at is called the growth accounting equation. It's saying something incredibly important. On the left-hand side, we have the overall growth rate of output in the economy, the rate of economic growth. And on the right-hand side, we've been able to divide that growth up into 3 distinct factors. The first factor, growth in total factor productivity. The second factor, growth in the capital stock. The third factor, growth in labour. But note the extent to which either the growth in the capital stock or growth in labour influences the economic growth rate is going to depend on the value of alpha. So that value of alpha is actually pretty important in this analysis. But it's really the main idea I want to get across here. An economy's growth rate, using this growth accounting technique, as long as you're able to measure all of these variables, can be divided between total factor productivity growth, capital growth, and labour growth. And it's using this equation that economists go out and examine the economic growth history of various economies to try to determine in the historical record what's been most important for an economy's actual growth. Is it total factor productivity? Is it capital? Is it labour? Is one of these factors more important than the other? This technique actually enables you to conduct that exercise. And this exercise has been done very, very frequently. You won't have to look too far in the economic literature to find examples of exactly this. So here's one study from the research literature that I wanted to bring to your attention, which has done exactly what I described in the previous slide for a variety of economies. And I want you to note the following. Over the time period that we're looking at, that's the time period where those 5 economies experienced their initial and often quite spectacular periods of economic growth. And look what was most important: capital. The share of capital in driving economic growth was dominant for these economies in that period. And total factor productivity, less so. But when we look at the more mature economies with much longer histories of economic growth, we'll see that, yes, capital was important, but for these economies, the most significant factor driving their economic growth, total factor productivity. This is exactly what we concluded from our 2-dimensional production function, and it's our first important lesson about economic growth. So let's just stop and summarise a little bit about what we've done. We've actually done a lot, we really have. So the way macroeconomists approach the study of economic growth is to do so in a very systematic, simplified fashion, building on the analytical tool of the production function. A very simple representation of something that we know in the real world is incredibly complex. The bringing together of capital and labour and many, many other factors in a way that produces output. A key characteristic both of real-world production and this analytical tool, the production function, is the idea of diminishing marginal productivity. And our first and very important lesson about economic growth is that if you are talking about an economy that's beginning its process of growth, so that's starting from a base of a relatively low capital-labour ratio, then the path to economic growth, to significant growth, in other words, in per capita income, is to boost that capital-labour ratio. If you are talking about an economy in a different stage of its development, where it has already achieved a relatively high capital-labour ratio, the path to further economic growth is not going to be growing the capital-labour ratio, it's going to be through total factor productivity. In this lecture, we're going to explore one of the most important and famous models in the entire history of macroeconomics, a model which sheds light on some key fundamental features about economic growth and indeed helps clarify for us what we even mean by economic growth. Before we do that, let's just recap what we learnt from our previous lecture. The very important implication about how the path to economic growth can be different for different economies depending on their starting point. For economies with a low capital labour ratio, then it's possible to obtain a relatively large increase in per capita income through growing the capital labour ratio. But diminishing marginal productivity means that that's not necessarily appropriate for an economy that's beginning with an already high capital labour ratio. There, the path to further increases in per capita income will be total factor productivity. These themes will actually be important as we develop this particular model of economic growth. Now, the model of economic growth we're going to outline is known by various names, sometimes the Solow growth model, sometimes the Solow-Swan growth model, sometimes the neoclassical growth model. And if you search the economics literature or look at various textbooks, you'll find that either of those three terms are used. I prefer the name the Solow-Swan growth model, and that's how I'll refer to it in this course, because it reminds us of the two scholars who developed this model. Robert Solow, one of the most famous and eminent economists that there's ever been, associated with MIT, and an Australian economist, Trevor Swan, who was based at the Australian National University. It's interesting that in the development of this model, neither of these two scholars actually collaborated. They were working entirely independently, pretty much at the same time, trying to answer the same question: what is the nature of the economic growth process and what fundamentally matters for that process? And came up with pretty much the same mode of analysis. It's quite a remarkable coincidence. It's not one that happens very often, but it's something I think we should recognise in labelling this particular way of thinking about economic growth, the Solow-Swan model. The model, as you'll see, picks up on a lot of the themes we've already been exploring, and it's remarkable because of its simplicity. It's a beautifully elegant model. It's elegant in how simple it is, how it just builds on some key foundation principles in economics, principles we've already explored. But it's famous because of a very surprising prediction that this model yields. It's a prediction that says the following: unless there is ongoing growth in total factor productivity, then growth in real per capita income will eventually come to a stop. It's a model, in other words, that predicts economic growth will eventually cease. It will cease unless something else happens, and that something else will be an increase in total factor productivity. It very much throws the focus on total factor productivity and clarifies for us how without that growth in total factor productivity, there is an expectation, as you'll see, that growth in per capita income will eventually come to a halt. In other words, economic growth without growth in total factor productivity can never be a very long run event. It has a finite lifespan. It's an incredible prediction. It raises all sorts of interesting questions. How can this be? And how can it be when we look at the historical record of so many economies, Western Europe, the United States, for example, that now have many hundreds of years history of economic growth? But you'll see the key is in total factor productivity. The beauty of this model is that it highlights what is the absolutely essential factor that needs to occur for there to be long-run economic growth. So let's begin, and actually a lot of this will be familiar because we're going to build on many of the concepts that we touched on in our previous lecture. We'll be working, as is appropriate for a model of economic growth, with the per capita production function, which we illustrated diagrammatically in our previous lecture. We can also represent it mathematically. This is just shorthand notation, and if you think about it, what you're looking at there is really just a mathematical representation of the two-dimensional per capita production function we worked with in our last lecture. So on the left-hand side we have real per capita output for the economy, which we know is the same thing as real per capita income. On the right-hand side we have total factor productivity, represented by A, by the letter A, and a function of the capital labour ratio. So it's telling us what we discovered from our diagrammatic treatment of the per capita production function, that what matters for per capita income is the capital labour ratio and everything else that gets collected in that total factor productivity term. In addition, we're going to make an assumption. Again, it's something we've seen before. And again, we're just making this assumption for the purposes of simplicity. We don't need this assumption to outline the Solow-Swan approach to economic growth, but it's going to be easier to outline the approach if we make the assumption that everyone works. And if everyone works, then per capita output can be written as Y divided by L. L is the number of people working, but in this case the entire population works. And of course we can think of that as well as being a measure of average productivity. This is a model where average productivity is the key to growth, and as you'll see in the long run, growth in total factor productivity is the means to achieve growth in average productivity. So here's a diagram that we have seen previously, the per capita production function diagrammatically now, where we have the capital labour ratio on the horizontal axis and per capita income or output or average productivity on the vertical axis. And again, let me emphasise, and this is actually going to be a very key part of the Solow-Swan story, please note that what we have built into this approach is diminishing marginal productivity. In this case, the diminishing marginal productivity of the capital labour ratio. And remember, and this is going to be absolutely key to understanding the logic of the Solow-Swan model, as the ratio of capital to labour increases, as there is more capital available per worker, the result will be an improvement in average productivity, an increase in the amount of output per person, an increase in per capita income, but that this occurs at a diminishing rate. And you're going to see very shortly just how important that notion of diminishing marginal productivity is to this particular way of thinking about economic growth. So far, everything I've described about the model is familiar. we'll now start introducing some new elements to think about. And the new elements arise because I want to ask the following question. Over time, what happens to the capital-labour ratio? What I mean by this question is, suppose you just sat back and observed an economy over time. Is there anything over time that is going to happen to that capital-labour ratio? Well, in fact, there are two important forces at work which over time will operate to lead to changes in the capital-labour ratio, and this happens without there being any intervention or indeed any decision-making going on in the economy. This is part of the nature of the capital-labour ratio itself. The first is population growth. An increase in the size of the population, which, remember, given our assumption that everybody works, means an increase in the size of the labour force. So we're going to use the letter L for our population, and all we're recording here is the tendency over time for populations to get larger. If that was the only thing going on in this economy, and for the purposes of this first observation, let's assume that that's the case. It's an economy where nothing else is happening other than growth in the population, then the capital-labour ratio over time as the population grows must fall. Because we're not changing the capital stock, but we're growing the number of people using that capital stock. So over time, there's a natural inbuilt tendency for the capital-labour ratio to fall, assuming nothing else changes, brought about by population growth. There is a second factor at work, which over time will also lead to a fall in the capital-labour ratio, and this is depreciation. Now, by depreciation, what I'm referring to is the tendency for the capital stock to wear out through time simply because of use. In our notation, the way we can represent depreciation is there will be a fall in the capital stock, which means if that was the only thing that was occurring in the economy, we just sat back and observed an economy where the only thing that was going on through time was depreciation, we would be observing a fall in the capital-labour ratio. Now, in reality, these things probably happen simultaneously, but they both have the important implication that over time there are forces at work due to the nature of the capital-labour ratio implying that that ratio will diminish in value through time. For example, let's think about the following. Suppose, and I'm going to introduce some notation here, suppose we have a population growing at a particular rate, and I'm going to use the letter lowercase n as my shorthand notation for the population growth rate. Let's suppose that the population is growing at a rate of 1% a year, which we'll represent by the number 0.01. And let's suppose at the same time there is a depreciation rate, and I'll use the letter D to stand for the depreciation rate. Now, this is the proportion of the capital stock that wears out through use over a particular time period. Let's suppose that's 5%. Over a year, perhaps, 5% of the capital stock can be expected to wear out. What do these two factors, population growth and depreciation, imply for the capital-labour ratio? Well, let's do it this way. Depreciation means over this particular time period we can expect the capital stock to diminish by 5%. And over this particular time period, population growth implies that labour will increase by 1%. The combined effect of these two forces, depreciation and population growth, will be that over this time period we would expect that the capital labour ratio will fall by 6%. Let me now turn to investment. We've spoken about investment previously in our discussion of the national accounts and gross domestic product. What I want to think of now is investment very much as a flow of expenditure undertaken by firms, and let's focus on their purchase of plant and equipment that adds to the capital stock. And I want to identify two distinct types of investment. First, replacement investment. As the slide indicates, when we speak about replacement investment, we're talking about firms undertaking expenditures by exactly the amount that will offset the combined forces of population growth and depreciation. The point about replacement investment is that it keeps the capital labour ratio from falling. It doesn't grow the capital labour ratio. All it does is exactly offset the combined effects of population growth and depreciation. So replacement investment is the investment undertaken by firms to ensure that the capital labour ratio is not diminished over the course of a time period. The second type of investment is going to be called net investment. Net investment is any investment that takes place, any expenditure by firms on plant and equipment, in other words, over and above replacement investment. So you could think of net investment, and I'll use NI for net investment and RI for replacement investment. And if you just see me write the letter I on its own, that's total investment. Net investment will equal the difference between total investment that takes place and any replacement investment that takes place. The effect of net investment, if it occurs, and it doesn't necessarily have to occur, and we'll talk more about that very, very shortly, but the effect of net investment, if it occurs, is to grow the capital labour ratio. Because if you're undergoing some net investment, you've already met your economy's replacement investment needs, you've already offset depreciation and population growth, and so this is expenditure over and above what's needed to keep the capital labour ratio steady. This is expenditure that is actually leading to a growth in the amount of capital per person. So I'm going to write the following expression. Now again, this is just mathematical notation. This is just shorthand. It's just a convenient way of recording the discussion from the previous slide. Now everything from here on is in per capita terms. So on the left-hand side, when I write I divided by L, what I'm recording on the left-hand side is total investment. Often this is called total gross investment. Now I'm just going to write it like that. I'm not going to write per capita because it gets a bit redundant after a while, but be aware that what we're actually measuring on the left-hand side there is total gross investment on a per capita basis. On the right-hand side of the equal sign, we have our replacement investment. I'll just write INB for investment. Remember, the crucial thing about replacement investment is that it's designed to keep the ratio of capital to labour constant. It's offsetting population growth and depreciation. On the right-hand side, on the final term on the right-hand side, delta K on L, the change in the capital labour ratio, that's our net investment on a per capita basis. Remember that net investment is the only thing that will actually lead to a change in the capital labour ratio. So to remind us of that, to remind us that what net investment does is to change the capital labour ratio in this expression here, instead of writing net investment, NI, I'll write the effect that it has, which is to change the capital labour ratio. Now for a moment I want to focus on this replacement investment, because I want to think about it in a very, very particular way. And I'm going to start with the end point, in fact. What I'm going to argue is that we can write a very, very simple relationship between replacement investment and the capital labour ratio, where the amount of replacement investment that takes place over a period is equal to the sum of depreciation plus population growth multiplied by the capital labour ratio. The easiest way to think about what that expression is actually saying is to think about the following two situations. Suppose you have a given ratio of capital to labour. So think of that as the starting point. You start with a particular ratio of capital to labour. And we're just going to hold that fixed. Then if you think about it for a moment, you're going to need, for that given capital labour ratio, more replacement investment. So more replacement investment is needed if the depreciation rate and or the population growth rate is higher. So if you start off with a particular ratio of capital to labour, how much replacement investment you are then going to need is going to depend in a fundamental way on how fast the population is growing and on how quickly the capital is itself wearing out. The second observation I want to make about this is to think about the following exercise. Suppose you have given values of the population growth rate and the depreciation rate. Then, again, thinking about it logically, more replacement investment in that case will be needed the higher is the capital labour ratio. If you have more capital per person, then you're going to need more replacement investment for given rates of population growth and depreciation. Both those observations are consistent with this little equation here. For a given value of the capital labour ratio, the higher is depreciation and population growth, the more replacement investment is needed. For given depreciation and population growth, the higher is the capital labour ratio, the more replacement investment is needed. This little mathematical expression simply summarises the two possibilities that I've identified in the top part of this slide. I now want to remind you of an important theme from our lectures on gross domestic product. This is the sense in which there is an equivalency between investment and saving. And you'll recall that when we looked at the national income accounting identity, we saw that there was this relationship between investment and saving. Now, There we looked at what's called an open economy, and we saw that the relationship between investment and saving is fundamentally tied up with the relationship between imports and exports. I'm going to simplify things here and assume that either imports equals exports, so we have balanced trade, or that this is what is called a closed economy, an economy that does no trade. Now, neither of those two assumptions are needed for the Solow-Swan model, but again, having those assumptions in place will greatly simplify the analysis. I'll ask you in one of the exercises to use the national income accounting identity under the circumstances I've described and demonstrate for yourself that in either a balanced trade situation or a closed economy, it must be the case that the nation's saving is equivalent to the nation's investment. But I'd like you to think about this at a much more intuitive level and to ask the following question. Where does the economy obtain the resources it needs for its investment? Now remember, investment are resources that are used now to procure a benefit in the future. Where do those resources come from? They must be resources that are withheld from current use. They must come from saving. They can't come from anywhere else. So in this Solow-Swan framework, when I speak about investment, a very important consideration is where does the economy find the resources for that investment? The answer must be from saving, because saving represents the resources in the economy that are not immediately consumed, that are not used to meet immediate needs. Those resources are therefore available for investment. In practice, how this happens is that savings flow into the financial system and are then lent out to businesses who use those savings to finance their investment. So whilst I don't want to have a formal model of the financial system in this framework, again, that is possible, think about that there is an institutional structure out there, a financial system, if you like, that ensures that the resources that are made available through the act of saving flow to firms who then have access to those resources to use for their investment purposes. So the key point here is investment draws on the resources that are made available through saving. Which means in the Solow-Swan framework, we need to think a bit about saving and how those resources actually are made available for investment. And we're going to use a very simple hypothesis about saving. The hypothesis about saving is that the saving per capita that takes place in the economy is some constant proportion of per capita income. And I've written it mathematically in this expression here. An example might be to have a value of theta, so that's the Greek letter theta, and we're going to call that the economy's saving rate, the proportion of per capita income that is saved. That might be a number like 0.4. What this is saying is that in this particular instance, 40% of the nation's per capita income is withheld from current use and used as saving. Now remember, the production function, which we've seen before, can be thought of as showing not just production but also income. What I've done in this slide is to put a second line on this diagram that relates to saving. So this red line here is equal to 40% of per capita income. So how do you read a diagram like this? What's actually going on? Suppose the economy had a capital labour ratio equivalent to that point. Then that capital labour ratio will produce, or allow the economy to produce, is perhaps a better way to think about it, per capita income of 2.5. 40% of that per capita income is going to be saved, and we can read that from this red savings function, as it's often called. So we start with the capital labour ratio. That tells us how much income will be generated in this economy. And given our very simple view that saving is some proportion of income, that tells us how much saving will be generated in this economy. Remember, saving frees up resources. Saving frees up resources that can then be used for investment. So let me summarise what we've done so far. We've actually done, again, an enormous amount, and we're about 3/4 of the way, in fact, through the Solow-Swan model. Because what we've got here is a representation, simple representation, of saving and investment in the economy. And then we have a view of investment, and it can be either replacement investment or net investment, that tells us something about the circumstances in which the capital labour ratio can grow. Growth in the capital labour ratio, remember, is one path towards economic growth. So it's all summarised in these two forbidding equations, but really this is not really complicated mathematics. This is just shorthand notation where we've conveyed a great deal of information. So what information do we have here? On the left-hand side, total gross investment. Total gross investment can be divided across the two forms of investment: the replacement investment that stops the capital labour ratio from falling, and the net investment that actually leads to change in the capital labour ratio. We have a link between investment and saving, with saving freeing up the resources that are used for investment. And here we have a little hypothesis about how many resources in fact will be freed up through saving. Those resources will be some constant proportion, some constant fraction of per capita income. So there's a lot going on in that expression, but what I've done here is just pull together the discussion from the previous few slides to give us a pretty comprehensive picture of how the Solow-Swan model treats investment and saving. Now I want to focus on investment. Have a look at this expression here, which simply takes the information from the previous expression and rearranges it in the following way. What we learned from the previous expression is this: the amount of net investment, the investment that enables the capital labour ratio to change, is going to be equal to the amount of saving generated in the economy minus replacement investment. The way to think about this is saving frees up resources. It's resources that are not immediately used. Some of those resources are going to be devoted to the replacement investment that's needed to offset depreciation and population growth. If there are any resources left over, those resources can be used for net investment, and it is the net investment that enables the capital labour ratio to change. So to summarise, For the per capita capital stock per person, the capital labour ratio in other words, for that to change, there has to be some resources left over from per capita saving after what is needed for per capita replacement investment has been deducted or has been used. This is a key slide. It's very important that you understand what's going on in this slide. It's summarising an enormous amount of information, but it is information that's going to be absolutely key to understanding this Solow-Swan approach to economic growth. What we now have is a very important principle about the circumstances in which the amount of capital per person, the per capita capital stock, the capital labour ratio in other words, when can that possibly change? And it's a story about saving and investment. It's a story about there being some resources left over from saving after we've taken care of our replacement investment, with those resources then being able to be used for net investment, and in doing so grow the capital labour ratio. Keep that in mind as we go through these next few slides, and that's going to be a very important notion for us as we develop the Solow-Swan approach model of economic growth. So as we have seen, we are going to have a very simple hypothesis, a very simple theory of saving, that the economy's saving is a constant proportion of its income, so that on this particular diagram I can draw both the per capita production function and also what's called the per capita savings function. In other words, you can tell me any particular capital labour ratio and I'll be able to tell you by reading off this diagram what the corresponding per capita income will be. And once I know per capita income, I can tell you what the corresponding per capita saving is. And remember, once I know how much saving is going on in the economy, I have a measure of the resources that are available for investment. One more piece of information that I need to add to the analysis, and then in fact we have a pretty comprehensive picture of the entire economy. The final piece of information I need is a line which tells me how much replacement investment is going to be needed for each and every level of the capital labour ratio. And that's this, the replacement investment schedule, as it's called. You remember the argument about why it has this particular form, that the amount of replacement investment is going to depend both on the size of the capital labour ratio, but also on the rates of population growth and depreciation. And in an exercise, I'll ask you to vary some of those terms and see what happens to this replacement investment line. The way to think about the replacement investment line or replacement investment schedule is it tells us what needs to happen at each and every level of the capital labour ratio, given the rates of population growth and depreciation, what has to happen to exactly offset the effects of population growth and depreciation, what has to happen to stop the capital labour ratio from falling. So it's a bit of a guideline, if you like. It tells us something about the resources that will be needed for each and every capital labour ratio to stop that capital labour ratio from falling. And now I want to identify for you one of the most important, certainly one of the most famous concepts in economics, and it's at the absolute heart of this Solow-Swan approach. This is a situation known as the economy's steady state. What is the steady state? As the name suggests, it's a situation where if the economy was to find itself in this position, in this situation, nothing would subsequently change. In this analysis, the steady state is identified with this particular point on the diagram, which I'll call point, I'll call it point A asterisk. It's nothing to do with total factor productivity. It's just a label I'm attaching to that point. What I'm saying here is that should the capital labour ratio happen to be at that particular value, let's call that K on L star. Now, I'm not going to address whether the economy will be at that point. We'll come to that very shortly, but let's just suppose it was. That for some reason, the economy's capital labour ratio was at that point, K on L star. There would be a corresponding level of per capita income in the economy through the production process given by Y on L star. That would generate a flow of saving that exactly corresponds to what the economy's replacement investment needs would be at K on L star. So to repeat what's going on here, if the economy happened to find itself at a point consistent with A star, in other words, if its capital labour ratio was this K divided by L star, there will be a flow of savings being generated at that particular point that would be exactly equivalent to the economy's replacement investment needs. No more, no less, but exactly equal. What does that mean? It means there will be no change to the capital labour ratio. We've exactly offset the combined effects of population growth and depreciation, but we haven't any resources left over from saving once we've done that to engage in any net investment. So the capital labour ratio would not change, and the economy, unless something should happen to alter these circumstances, would remain in this position, hence the term the steady state. This is an economy where there is no economic growth. There is no change to per capita income. It really, literally is a steady state. The obvious question to ask then is, well, so what? So there is this steady state. It's just a theoretical possibility. Is there any reason to believe that an economy might find itself in such a position? Well, in theory, the answer to that question is unambiguously yes. And to see why, suppose the economy wasn't at the steady state. And this is a very common technique used by economists to take a situation different from the one we are actually considering and seeing if that makes any difference. So let's consider two circumstances where we're not at the steady state. The first circumstance will be, suppose the economy, for whatever reason, finds itself with a ratio of capital to labour, let's call it K divided by L prime, which is actually higher than the steady state. What would happen then? Well, I want you to look carefully at this diagram and note the following. Should the economy's capital labour ratio be at this particular point, with a very high capital labour ratio, the economy's need for replacement investment is going to be quite high. A lot of resources will need to be devoted to replacement investment to offset the population growth and depreciation. Where are those resources going to come from? Well, we have a problem. We are getting some of those resources from saving, but not all of them. We have this gap. The economy's need for replacement investment exceeds the amount of saving that's being generated. This means we can't fully offset the effects of population growth and depreciation. Not possible. We don't have enough resources to keep the capital-labour ratio from falling. And that's what would happen next. The capital-labour ratio would start falling. As the capital-labour ratio falls, our need for replacement investment also correspondingly falls. And as the capital-labour ratio falls, the per capita income being generated in this economy also falls. And as a consequence, less resources will be needed for saving. So you can see what happens. We are taken to the steady state. Once you're at the steady state, the process will stop. There'll be no further reduction in the capital-labour ratio. We will be literally at the steady state. So what's the key message from this analysis? Should the economy find itself with a capital-labour ratio which is higher than the steady state, insufficient saving will be generated to meet the economy's need for replacement investment, the capital-labour ratio will fall, and the economy will find itself in that steady state. What if we had the opposite circumstance? And this is one I really, really want to emphasise. This is crucial. What if the economy found itself with a capital-labour ratio, let's call this one K on L double prime, which was to the left of the steady state? Well, once again, we have a gap. But it's a different sort of gap to the one from the previous slide. What we now have is a situation where if we have the capital-labour ratio K divided by L double prime, we have a situation where the saving generated by this economy is going to be larger, as you can see, larger than its need for replacement investment. What does that mean? It means there are resources left over for net investment. So net investment can be a positive number, which is what I mean by that little expression there. What does net investment do? Net investment grows the capital-labour ratio. And what does growing the capital-labour ratio do? It grows per capita income. As the capital-labour ratio grows, the economy's need for replacement investment grows, but so does its saving. And this process continues until once again we're in the steady state. Think about what we've shown in this slide. What we've shown in this slide is, in fact, economic growth. And that's one of the main contributions of the Solow-Swan model. It actually clarifies for us what we mean by economic growth. Economic growth, this moving around the production function, this increase in per capita income, is actually an economy moving towards its steady state. When we see an economy growing in this framework, we are looking at an economy that has an actual capital-labour ratio below the steady state. And what we call economic growth is actually movement towards the steady state. When you think about what we've shown here, that's quite remarkable. Look at the diagram. There are two axes, three lines, some very simple concepts. In particular, the link between saving and investment that we know from the national income accounting work that we did previously. This simple framework, two axes, three lines, and we now have a very profound insight into the nature of economic growth. When we see economic growth, when we see growth in per capita income, we are looking at an economy travelling towards its steady state. That's actually a pretty important and powerful message, I think, that comes out of this framework. However, it is troubling in one respect, and you've probably thought of this already. This is a series of lectures on economic growth. This is a series of lectures that began with an observation for the United States that's repeated in a wide variety of economies around the world of what looks to be a continuous process of economic growth over very long periods of time. Why is it that in the United States, Western Europe, Canada, Australia, many other countries, why do these economies have such long histories of economic growth? Why aren't they reaching their steady state? So many people look at the Solow-Swan model and scratch their heads a bit and say, well, look, that's all very interesting, it's a very nice model, I can see why you like it, but it can't really help us, can it? Because this is a model that predicts an end to growth. This is a model that says, well, you just sit back and wait, and eventually per capita incomes will stop growing. But my view is that's the wrong way to think about the contribution of the Solow-Swan model. What the Solow-Swan model shows us is that unless something changes in this framework, the inevitable result is a steady state and an end to growth. The fact that we see so many instances in the real world of long-run growth tells us that there must be something else going on, something else that means the attainment of that steady state is not yet happened. Now, there are two obvious candidates for that. One probably not as important as the other, but I'll deal with that one first. And that is, what if there's an increase in that savings ratio, that number theta? What if it went up from 40% to 50%? Would that make a difference? Well, let's conduct an experiment. Let's take an economy initially at a steady state in A star. And let's now increase the savings rate. How this happens is not really important for this demonstration. It may be that people themselves make a conscious decision to try to put aside more resources. There might be a government here who mandates in some way that more resources are withheld. It doesn't really matter. For whatever reason, this is a society that has decided to withhold more resources from current consumption, therefore to make those resources available for the purposes of investment. So we start at A star, and then we increase saving. So the savings rate moves from theta 0 to theta 1, from 40% to 50%. So the saving function shifts up. What implication does this have for the economy? Well, what you can see straight away is a new steady state. A star is no longer the economy's steady state. The economy's steady state, once the savings function has shifted up, becomes B star. What does that mean? It means that that capital labour ratio that was initially associated with that particular steady state is now associated with a flow of saving which is greater than replacement investment. We've seen what happens under these circumstances. We know that under these circumstances, where there is more saving than what is needed for replacement investment, that net investment can now take place. The capital labour ratio can grow. As the capital labour ratio grows, so does per capita income. You get some economic growth. and the economy then travels. It'll travel to that new steady state. So one way in which an economy can grow once it's reached a steady state is to increase the savings rate. However, it's not quite as simple as that. It's not quite as simple as that for two reasons. One is that eventually we get back to the steady state. It's a new steady state. It's a new steady state which has a higher capital labour ratio and consequently a higher level of per capita income than we had originally. So in some sense people are richer, but once you get to the steady state, growth stops. So this increase in saving gives you a temporary period of economic growth, but it doesn't give you economic growth forever. The second important consideration here is there are limits to how many resources can be put aside for the purposes of saving. Current needs have to be met. It would be a very foolish society indeed that saved all of its income, had nothing to meet its current needs, and so this process of increasing the savings ratio as a means of getting at least some temporary growth, there has to be limits to how often that can take place. There are limits to how sensible it is to increase the savings rate. What we've done so far in this lecture is develop the structure of the Solow-Swan model of economic growth. An extraordinarily famous model in the history of economics. As you've seen, it gives us a great deal of insight into the process of economic growth. I should say before we go much further that there's been a great deal of work refining this model, building on it, and introducing a whole range of real-world features that has provided even more insight into economic growth. And if you go on to study more macroeconomics, you'll certainly encounter those more advanced versions of this model. But what I'm demonstrating for you here is the model as it was originally formulated, which, simple as it is, provides us, I think, with some really important insights into the process of economic growth, insights that I'm very keen to share with you. So let's just summarise a little bit. There's the model, and as we've seen, the absolute key to understanding the model is the notion of the steady state. You can think of that point, and this is probably not a bad way to think about it, as what is sometimes called an attractor. What I mean by that is that there are forces in the economy that are pushing the economy towards that steady state. It doesn't matter if your capital labour ratio is to the right of that point or to the left of that point. As we've seen, there is a tendency for the economy to be moved towards that point. It could take many years, but you're going to get there. The other important thing to note about the steady state, about the attractor, is there's no growth if you're in the steady state, and that is no growth in per capita income in the steady state. And why I think that is so important is because it clarifies for us what we mean when we talk about economic growth. That growth in per capita income is actually the economy growing to the steady state. But as we previously discussed, that has with it the implication that there must come a point in time where growth stops, where the resources that are made available through saving cover replacement investment, but no more. And that raises this interesting issue of, well, why do we observe so many instances of long-run growth in the real world? We looked at one possibility, a growth in the proportion of income that's saved, and we saw that that wasn't a complete explanation, because whilst that would shift the steady state to the right, and as a consequence lead to some economic growth, that would only be temporary, because eventually the new steady state would be reached. So how then do we explain continuous long-run growth? How do we explain growth in the United States, Western Europe and other economies going back hundreds of years? Well, the Solow-Swan model tells us where to look, and that's, I think, its main contribution. It tells us that we have to look to forces that are shifting that steady state continuously to the right. Because if the steady state is shifting continuously to the right, in other words, if that steady state capital labour ratio is becoming increasingly larger, and that's always happening, if there's continuous growth, in other words, in that steady state capital labour ratio, maybe economies never catch up to the steady state. Maybe they're growing towards a moving target. And when we see hundreds of years of economic growth, what we're actually seeing is the economy trying to get to the steady state but never quite reaching it, because the steady state itself is growing. And where can that come from? Total factor productivity growth. So let's just backtrack so I can tell you the story in a bit more detail. Suppose an economy is at its initial steady state at A star. We know all about the characteristics of that steady state now. But suppose there is growth in total factor productivity. What is that going to do? It's going to shift the production function upwards. What else is that going to do? It's going to shift the saving line upwards. But this is a different shift to the one I had in the previous slide. This saving line will still feature the same savings rate. We've not grown the savings rate here. It's still 40% of income. The point is it's now 40% of higher income. So as the production function shifts up, so too does the savings function. What does this do to the steady state? We have a new steady state, B star. And now it's exactly the same story that we had before when we have an economy below the steady state. A star is no longer the steady state. B star is the steady state. We will have a gap between saving, which is now read off the new saving schedule, and replacement investment. Net investment will be positive, the capital labour ratio will grow, and we'll get economic growth. Why doesn't it stop in the new steady state? Well, it might, if that was the end of the story, but why should it be the end of the story? What if there is another increase in total factor productivity? I won't represent this on the diagram, but you can see, I hope quite logically, that that will once again shift the steady state to the right. And so on. Long-run continuous economic growth has to be associated with a process of continuous change in total factor productivity. Nothing else will do it for you, because everything else means you fall into the steady state eventually. But if your production function is always shifting upwards, and if it's always dragging the savings function up with it as well, so that the steady state is itself continuously growing, then economic growth may occur over very long periods of time. Simply put, you never get to the steady state because the steady state itself is growing. So let me summarise this. Economic growth at a fundamental level is going to require an increase in the ratio of capital to labour. It's going to require more capital to labour. And think about this as, in fact, the means of increasing labour productivity on average. You give workers more machines, they'll be more productive in an average sense. Secondly, if we want to increase the ratio of capital labour, we're going to need net investment. To get net investment, you need to have resources. You need to have resources left over from saving once the economy's replacement investment needs have been met. Now think about the implications of diminishing marginal productivity. Each time you increase the capital labour ratio by 1 unit, you do get some more output, you do get some more income, but you're getting it at a diminished rate. So you're getting smaller and smaller increases in output, smaller and smaller increases in income. So consequently, you're going to get diminished increases in saving. As you grow the capital labour ratio, you grow income, you grow saving, but both income and saving are growing at a diminished rate. Replacement investment, however, the replacement investment needs of the economy are growing at a fixed rate, and they're growing at a fixed rate which is determined by the rates of depreciation and population growth. So you've got a tension. You've got a tension between the extent to which there are more resources being freed through saving and the resources that are needed for replacement investment. The resources that are being freed from saving, as the capital labour ratio grows, they are increasing, but increasing at a diminishing rate. The resources needed for replacement investment are increasing, but they are increasing at a fixed rate. Eventually, this means a steady state will be reached. And the steady state will be reached when that flow of saving is just sufficient. No more, no less, but just sufficient to cover the economy's replacement investment needs. There's nothing left over for net investment. The capital to labour ratio stops increasing and the economy is at the steady state. The implication of that is there is no further growth in per capita income, which also remains at its steady state level. What does that tell us? It tells us if you want continuous long-run economic growth, you need to grow the steady state as well. You need to make sure you never catch up to the steady state. And in this framework, what that is going to require is a continual process of total factor productivity increasing. And when economists think about this and what this means for the real world, what we usually think about is technological progress. Technological progress which has happened at a sort of continuous rate ever since really the Industrial Revolution. It's technological progress that is almost certainly driving this process. So when we look at the chart that we began with, this remarkable observation that the rate of economic growth is not much different in the 21st century to what it was in the 19th century, we now know that that rate of economic growth over this long period of time must, at a very fundamental level, be reflecting improved total factor productivity, and over this long period of time, it's almost certainly related to technological improvements. And therefore, it's the rate of technological improvement, that continuous technological improvement, pushing total factor productivity up, causing the steady state to shift gradually to the right. That is what is ultimately underlying this incredible observation about economic growth.